Thank you. Today's topic of discussion is the development of laser tracking system, the history, the present, and the future. Next, please. So the content for today is the history and motivation, the motivation of laser tracking system development. Yeah, and then the second content will be on the 3D laser tracking system and the 5D laser tracking system, and also the laser tracker accessories, which help the laser to broaden the scope of applications, the present development API, and also our vision of the 3D metrology in the future. Next, please. Okay. Graduated from Wisconsin Madison, December 1981, and then joined NIST in January 1982. During that early 80s, there is general interest in the robotic area in the automobile and manufacturing sector. The general consensus is that the robot with the arm, like a human being, strong and agile, the vision system here, like an eye of a human being, and also the automation behind is the computer. So it looks like able to manipulate a lot of tasks where they're to replace the labor-intensive and repetitive jobs, and as a result, also improving the productivity and also accuracies. In 1982, Jack Welch, the CEO of GE, says that industrial robots and automation were basically the savior of the American industry. So indeed, during that time here, a lot of companies related to robots and vision systems formed, like Adapt, Invention, GE Fanuc, GM Fanuc also, and also Southport. Okay. Unfortunately, the robot experienced a lot of issues: accuracy problem, drift, repeatability, and also the vibration of the robot arm as it extends due to different load. Okay. So very quickly, the robot interest fade away. At the same time, there's a lot of trade issues, complaint between the suppliers and also the users of robots. That robot is not delivering the performance. Next, please. So my motivation while I was working on this is to develop a 5D, 6D laser tracking system to monitor the performance of the robot in both static and dynamic mode. Why is a 6D laser tracking system? Because robot is 6-degree freedom. Okay, so the idea was presented to Bob Hawken, Dr. Bob Hawken. He's the center chief that time, and basically agrees. And then in about 6 months' time, I came up with the first prototype of the laser tracking system. And then 3 months later, I also furthered that work to develop the 6-degree freedom laser tracking system. So here shows the, oh, here you go. Okay. So there's a heated packet laser going through the optics and then bounce off a flat mirror, which carries onto a 2-axis gimbal. So the mirrors reflect the beam to the target, which is a hollow corner cube that time. And then the target returns the beam back to the interferometer, and the beam would track the motion of this target moving in and out, up and down. Okay, basically to maintain interferometer tracking, which is very critical for the success of laser tracking system. Next, please. So, the result of that, there was a patent successfully issued in 1987. Okay, I myself and Dr. Bob Hawken are the inventors. The title is called 3D and 3-axis and 5-axis laser tracking system. Next page, please. Here, the patent shows the 2 configurations. One is the 6-degree freedom laser tracking system. In this here is 3-degree freedom laser tracking system. Unfortunately, that time here, because of the robot industry, the interest fade away. More interest focus on the 3D laser tracking system. Next, please. So I need to mention that about the time, there are also two other companies developing laser tracking system. One is the iTech, they're located in Connecticut. And I refer the system as quadrilateral tracking system. What it means is that it's using 4 independent laser tracking systems mounting on a common platform, like an optical table. Okay? And then commonly tracking on a single target. Okay, so 4 laser tracking beams tracking a single target. The purpose is for large contour mirror measurement. So another company is called Chesapeake Lasers. Since about the same time here, they developed this similar technology. I think they're funded by the Navy. But eventually, they sold the company to SMX, and later on, SMX sold to Faro, and Faro began making the single beam laser tracking system. Next, please. Okay, no, that's correct, that's correct, okay. In 1987, realized that I need to move the technology out from the government labs to industry. As you know, that there are a lot of exciting invention and developments come from the government labs. Unfortunately, most of them are actually shuffled in the shelf and basically left untouched, which becomes a waste. So I realized the need to move to industry. That's why I left NIST and formed API. So at the same time, I successfully obtained exclusive license from NIST, okay, to commercialize the laser tracking system. In 1988, 1 year later, I used my own money to build the first laser tracking system. Unfortunately, Boeing was very interested in that subject, and then led by Dr. John Palmetier. Is John Palmetier here? Ah, okay, over there. Hi, John. Okay. And so John, along with Scott Sandberg, okay, led the team to look at the use of the laser tracking system, okay, compared to the conventional techniques of using the template, trigger fixture, and CMM. Okay, to see whether tracker, the usefulness of tracker replacing those technology. I think that's a result after 9-month study that basically changed the aircraft industry from using the conventional technique to the use of laser tracking system. I think that is really the beginning of the recognition of the laser tracking technology. So orders began to come, and Boeing, Lockheed Martin, the Navy, and the University of Tennessee. Unfortunately, API at that time was only 2-man show. I myself was another engineer. So I was looking for investors, but unsuccessful during that time. So as a result, then I licensed the technology in 1989 to Leica. That time it's called Will and Kern, which is a surveying instrument company. And then Will and Kern become Leica and Hexagon of today. Next, please. So after the licensing, I spent around 3 years' time to support Leica to build a laser tracking system. So I passed all the hardware, design, software, plus the methods of calibration of laser tracking system to Leica. At the same time, help them to promote the tracking technology throughout the world. So if you look at the earlier model, the API laser tracker is we call generation 1. The laser in the front is underneath, shooting through the gimbal. This is a XY, this is a 2-axis gimbal, AC axis and EL axis. And there's a mirror there. So the laser through the gimbal into the mirror and it shoots out and pointing to the target. So if you look at the Leica system, here that comes called the Smart 310. Basically, it's the same design with the laser underneath here, shooting through the gimbal and off from to the camera. So the difference is that they have a cone here which hides the cable inside. So basically, they're the two same design. Next, please. So from robotic metrology to CNC machine metrology, since the licensing, API turned to focus on developing a complete suite of advanced machine tool metrology sensors, which we call WINNER MTC, machine tool calibration. So our focus turned into CNC machines. Then we create 7 modules of metrology sensors. I think a lot of you heard of the ball bar. Okay, the ball bar was invented by Jim Bryan of Lawrence Livermore Lab. And I saw the design. That was very complicated to use. So I modified the design to the existing design, which make it much easier to install. And I think Reneshaw later on saw the design, and basically they did a very good job in basically making a lot of ball bars. But they say, no, of course, API also makes ball bars too. So the second module is we call the multi-degree freedom laser interferometer. Typical laser interferometer is 1D, one dimension, okay, measure the linear travel. But the API invention that you can go up to 6-degree freedom measurement, meaning that when the machine travels in a long axis, it experiences 6-degree freedom error. It's not just one. So that means it also has straightness, horizontal, vertical straightness error, pitch, yaw, and roll information. So all those errors, totally 6-degree freedom, is what this laser system can capture. So it's a further advanced laser system. Swivel check for measuring all the A, B, C axis, rotary axis of the machine. Spindle dynamic, looking at the spindle runout of the machine. Thermal drift of the machine, which is very important. In fact, people always look at the static accuracies of the machine using the 1D laser, when in fact, the machine thermal drift is actually a pretty large error of the machine. And then you need to really look into it and do methods to compensate for that. Another one is the compliance gauge. The compliance gauge is actually looking at the machine deformation due to heavy cutting load. So when your machine cuts the part, you actually you exert a very large cutting force, as much as 1,000 pounds. Okay, that caused the whole column in the machine to deform. So a lot of times people do not look into those kind of problems. And then we have a surface profiler looking at the flatness of the granite table or the machine table. So from linear measurement to rotary, from static to dynamic, and looking at the machine thermal deformation, and also the force cutting deformation. Okay, here's a very complete suite of machine metrology instruments which API developed. I think we're the only one in the world that have this complete suite of products. So if you're interested in this topic, and yeah, please come and talk to us. We will go through all these things with you. Next page, please. So you look at the history of laser tracker development and API as a company development, they actually largely go in parallel. From the beginning of the company, what happened? From the beginning of the company in 1987 all the way to the present. And some of the major development of the laser tracking systems are highlighted here. Okay, good. I can push this. Thank you. So, as I said, we never stopped developing advanced tracking system technology, even though that time we licensed the Leica. So in 1999, which is 10 years later, after the licensing, we came up with a new model we call T2, which is smaller, more compact, more accurate, and lower cost. So we introduced to Leica. We believe that with this new T2 technology, that the tracker can penetrate into markets like automobile, shipyard, robotics, fabrication of large parts, etc. Unfortunately, Leica didn't agree with us, and so as a result, our collaboration ends after 10 years. And the API began to build laser tracking system in 1999. Okay, the second generation is actually revolutionary and also challenging. Okay, the idea is that all the optics now, instead of the laser underneath the gimbal and reflecting off a flat mirror, we eliminated the flat mirror, put everything right in the laser head, right here. So all the optics, the electronics, and control are in the laser head. So that is very challenging. So first of all, how to deal with the heat problem. We all know that heat in a precision instrument is very, very difficult to deal with. Where do you put the heat source? So we took a very challenging concept that let's put the heat source right in the center of the gimbal, okay? So the idea is to minimize the geometric distortion due to heat effect. And turns out the idea is true. So we have at least 2 companies studying this concept, and turns out that, yeah, putting the heat source right in the middle, minimizing the full distortion of the system. Okay. Another thing is that if you notice that our design here, this is a one piece of aluminum we call unibody. Okay. If the heat source of the laser is right in the middle of this gimbal here, then any heat would carry through this body very quickly and evenly, so helping to dissipate the heat at the same time maintaining the geometric stability. We use a 3-piece design because we don't want it to be too complicated. So there's only 3 pieces: the base, the vertical frame, and the laser source. Okay. At the same time, we try to eliminate any additional component to try to bolt on and screw onto it, because we want to maintain stability. That's why here that the unibody design and also the 3-piece design for stability and rigidity. But at the same time, it makes the manufacturing very, very complicated. Okay, still we're able to do that. The fourth challenge will be the servo system here. Instead of showing a mirror, which is much lighter, now you're talking about showing an entire laser head. You want to maintain the same tracking agility, and that's why it becomes very challenging to the optics, to the servo system here. The fifth is that we use the air over design, where we have slightly pulled the air from the environment through over the body of the laser head. Okay, keeping the laser head very, very cool and reaching the thermal equilibrium with the environment. So this also worked very well. One thing that I want to point out is that all the trackers right now come with ADM and interferometer, and some trackers now, because the ADM is getting more and more accurate. ADM stands for absolute distance measurement. Okay, IFM is the interferometer. Okay, that's the initially in the initial invention where we start with the interferometer. Okay, of course ADM is getting more and more accurate, and a lot of systems for lower cost, okay, would have trackers without interferometer. But I would like to point out the importance of the interferometer. If you look at this, having an interferometer in the laser tracking system is the only system, only 3D portable system that carries the first dimensional measuring standard. Interferometer is a dimensional measuring standard, first tier dimensional measuring standards. What it means is that you can do measurements, you can always check the accuracy of your measuring system against the same measurement, but purely along the interferometer axis. Okay, so in that case, you can establish traceability. Now, unlike CMMs, step gauges, for instance, I call them comparators. What does it mean? If you want to look at the accuracy of a CMM, what do? You bring an interferometer to establish, to calibrate the accuracy of the CMM. But once your interferometer is removed, the CMM is actually a comparator. Okay? So there's no first tier dimensional standard in it. Same thing as your step gauge. Step gauge is 1D comparator. CMM is a 3D comparator, that's all. Okay? So I think the importance of that, having an interferometer built in the system is quite critical. In case your industry rely on this traceability, I think there's a certain value in there. So some of the major tracker manufacturers, okay, everybody know Leica, Faro, API, and there's a new company called Chotas. They are from China. Around 3 years ago, they started introducing their laser tracker. So right now we have at least 4. I know there's the 5th coming out, okay? But yeah, there will be more and more companies producing laser trackers, okay? But trackers, we all know, that we're very familiar with laser tracker. It's basically a very good three-dimensional portable measuring tool. But they have limitations. For instance, line of sight. You need to maintain line of sight, otherwise you're not able to finish your measurement. It's also difficult to capture the fine and recessed details because you always have SMR that you need to manipulate. The size of the SMR is cannot be small enough to measure a lot of fine details, okay? Sometimes unsafe operation, sorry, hit the wrong key. Sometimes unsafe operation in some application. Also the SMR has a very limited angle of entrance, okay, only 15 degrees plus minus. So a lot of times you need to constantly manually move the target to face the laser tracker to continue measurement. And also it's basically a XYZ contact measuring device. But the advanced accessories, we call accessories, which work with the laser tracking system, really opens the scope of the usage of laser tracking system, which is very, very important. So the tracker usage goes beyond all these limitations which we'll talk about. Multi-degree of freedoms, measurements, unmanned operation, in-process integration, etc. Okay, the API accessory, it's not just API, but also our other vendors, they also have their own accessories, which I will introduce later on. The API accessories, like the active target, AT, okay, this small device here is a battery drive, self-closed loop device, where when your laser beam hits onto this device here, it always lock onto that beam. No matter how you manipulate your active target, the laser beam always stay locked on. Okay, it will rotate itself to always facing the laser tracking system. Okay. And then the second device is called STS, Smart Track System. The function is similar to the active target, that once the laser beam locks onto the target, it will stay capturing that beam, and no matter how you rotate, it always stays perpendicular to the incoming beam. But the other benefit is that it has IJK sensor built inside, meaning that it has the pitch, yaw, and roll information. Once the beam lock on, it generates those information, IJK information, to the laser tracking system. A V-probe, okay, basically a handheld probe, where we have a stylus. The ruby tip here is where the measurement occurs. So laser beam tracks here with the very wide angle acceptance and 360-degree roll capability. So it always maintains the measurement, final measurement at the tool tip. It's almost like a CMM. So it allows you to measure the detailed features and at the same time to avoid the problem of the line of sight. Okay, iScan 3D basically 3D scanning system here, handheld scanning system, and the device called i360 is very seldom mentioned. But in fact, if you look at the V-probe and the iScan 3D, they all have this i360 sensor there. So if you look at this, this is the i360 sensor. So what is this sensor? This is a passive sensor with 100 degrees pitch and yaw acceptance angle, and then 360-degree roll. Again, when the laser beam strikes to this target here, these internal sensors immediately generate the signal and send it back to the laser tracking system to complete the 6-stop measurement. Oops, did I miss one? Okay, that's good here. So let me give an example of how the active target and the laser tracking system together works. This is typically for CNC machine calibration or robot calibration. I need to mention Dr. Phil Freeman. I don't know whether he's here today. Okay, Phil is not here. Okay, anyway, now he's with in Boeing, South Carolina. Yes, okay, yes, South Carolina. So in 2008, API collaborating with Dr. Freeman, together we developed a technique called the VEC, Volumetric Error Compensation technique, for multi-axis machine tool, not just on CMMs or CNCs, but also robots, okay? His technique, I try to simplify his complicated mathematics into just 2 words. Basically, kinematic and statistical model that he created, okay? So kinematic model and statistical model, what does the statistical model do? It basically picks up all the residual but repeatable errors, which is not described by the conventional error described by a kinematic model. Okay, so if you look at one of the examples that in his mathematics, unlike a typical kinematic model where the machine is asked to move in a linear axis, let's say x, y, and z axis, he's basically asked the machine to generate random points which covering the entire machine volume. So points as much as several hundred points in space. Okay, if it is a multi-axis machine, let's say a 5-axis milling machine, then we also have the vectorial generation, okay, as a result of this mathematics. So basically, the tracker tracks the position of the SMR, in fact, actually, the active target. And then we're using a short tool and long tool to establish the vectorial information. So those points are randomly generated, okay? Again, unlike the conventional kinematic model where you command the machine move in X, Y, and Z, and there's a lot of areas that you're not covering. Okay, I have a video here. I can go to this video. There's a video here. How can I click this video? Click the next slide. Oh, okay, here you go, sorry. So this is the earlier model of the active target. And you can watch how the active target being manipulated, okay? So it always stayed perpendicular to the incoming beam, no matter how the machine moves, okay? So the new model here is basically totally wireless. Anyway, this technique is so successful that if we apply onto a 5-axis CNC machine, you will see probably between 4 to 5 times accuracy improvement. This is very, very significant. If you apply the same technique on robots, you would see somewhere between 12 to 14 times accuracies, which is very, very significant too, because robots are known to be inaccurate. Now with this technique here, you can increase the accuracy by 12 to 14 times, which is very, very significant. And so at this moment here, I just do a very rough estimate that over 1,000 machines are successfully implemented, probably more than 1,000. So a lot of machines right now, big machines, applying this technology is almost a must. Okay, here shows the improvements using this technique. Here we have a 5-axis machine, actually dual spindle machine. Those are real data, not simulated data. Okay, so prior to the VEC process, the error is 23,000 of an inch. After implementing that, the error here is all in this blue region, previously mostly in the red region here. Okay, is around 4,000 of an inch, which is around 5 to 6 times improvement. So those are actually real effects of it. And now we're using a different way to look at the error spread, okay? And then this is a before compensation. You can see the error spread over the plane. But when after you use the VEC compensation, then you can see the error pretty much clustered into the center. So this is a very, very effective technique. Thanks to Dr. Phil Freeman. Unfortunately, he's not here. In 1999, since we resumed production of laser tracking system, in about 2 years, we continue the development of the laser tracking system, and then we developed the 60 laser tracking with the combination of the STS and also the laser tracker. So again, the original motivation of the laser tracker invention was to develop the 6-degree freedom laser tracking system to study the robot, and also using that information to go back and control the robot, do a more accurate process. And so we're able to finally succeed in doing that in 2002. So this technique here basically create a 6-staff metrology system. You could use it for robot calibration, as I mentioned earlier, that you can see at least 12 to 14 times accuracy improvement, okay? Or you can use that to do machining, or using robot to do machining, and then replacing CNC machines, okay? Here is how showing the setup of error mapping a machine, a robot. Here, sorry, there's a video showing the early model of the STS manipulating and all the tracker tracks and generating all 6-degree freedom information. Okay, there's another project recently completed at University of Missouri Science and Technology where they applied the API 6-staff laser tracking system, the tracker and the STS right here, to control the robot end effector, which is a very, very successful project. I mean, if you're interested, you may contact the Missouri Science and Technology. Okay, again, the API is not the only company that have this so-called active advanced accessories working with laser trackers. In the case of Faro, they have their called 6 probe. Okay, is it the right name for that? Okay, anyway, there's a 6 probe. In the case of Leica, they have the TMAG, T-scan, B-probe, and T-probe. In the case of API, with the V-probe, the iScan 3D, and also the i360, which is the sensor. As I said, this the i360 is actually embedded on all those devices. Okay, so one of the main functions of those, what I call the accessories, is to capture the your raw information to complete the 6-staff calculation. So basically, in order to find the endpoints here, 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 or here, that we need 6-degree freedom information of this structure. There's a difference between the API technique versus the Faro and Leica technique. I'm not saying which one is good, which one is bad, it's just basically different techniques, okay? In the case of the Faro and Hexagon, you have a camera on the laser tracking system, and then monitoring those LEDs, okay, to detect the orientation of the sensor. Because of the use of the camera and the LED, so we all know that the sensitivity is dependent on the tracking distance, okay? So, so that is the technique that they choose. In the case of the API, the i360, which is on all the accessories, actually is a passive IJK sensor. As I said earlier, that when the laser beam hits the sensor there, the sensor, the internal sensor information immediately energized, and then send out its own value to the laser tracking system. So as a result, because the sensor is actually built inside the i360, it's not, accuracy is not distance dependent, okay? And you can reach as much as the range of the laser tracking system, which is probably around 50 meters. This is and showing how the i360 work in iScan 3D and also in the V-probe. So what's the present right now? Okay, API is certainly developing 2 very exciting devices. One is the 9D LiDAR, is a non-contact LiDAR system for part dimensional measurement. It has a range of 25 meters. We do have in our booth today that we have the 9D LiDAR. Another exciting development is called the ILT. LT stands for laser tracking system, okay, as we know. But the ILT is a new tracker design, which is even smaller and more compact than the one that we typically introduce. And it has basically the same high performance as the regular laser tracker. Because of its size, it is very suitable to carry up and down or to actually integrate into a system. The eye stands for two things. One is for intelligence, and the other is for integration. Okay, intelligence is actually through a high-end, high-density camera in the tracker itself, and then through the AI-enhanced algorithms to do a lot of imaging or processing. In fact, the ILT actually runs by GPU, not a CPU. So it's a GPU-run tracking system. And again, the GPUs, along with the high-end camera, creates a lot of AI image capturing and the processing ability. So again, we believe that this is the direction of the tracking system development. Add on a lot of artificial intelligence in the system and able to do intelligence, communication, and processing of information. And also in integration here, the IoT also have ability to interface to the machine process, which typically use is a EtherCAT. EtherCAT is also available on the IoT. Okay, so I think the third type of development going on is that the i360, as I mentioned earlier, and the ILT or the regular laser tracker, okay, together, combined with other advanced metrology instrument, okay, creating a new concept of dimensional metrology. And the paper was, the same idea was also presented by Jacob Hubert from Lockheed Martin. Is Jacob here today? No. Okay, not today, okay. So Jacob and Robert Murray present a paper with this concept in last year in the CMSC conference. So that's how I see the future of 3D metrology, okay? For some 40 years since the invention of laser tracking systems, the trackers has certainly, the demand for the tracker and the related technologies continue to grow, okay? And applications of the tracker from a manual operation began moving into semi or full automation. Tracker as a tripod standalone system now also move into integrated metrology system, which API refer to IM, integrated metrology, okay? Again, the I stand for two things. One is integration, the other stand for artificial intelligence, okay? That's how we see that tracker direction will be, okay? I have a short video here. This is the emulation video, kind of capture the concept of IMAT, but it doesn't have to be API equipment. It could be the ferrules, it could be the surfacer, it could be the hexagons. Here it shows the multiple metrology instruments. This is a 9D LiDAR here, and then here you can see the two i360. Okay, on the robot and on the robot on a linear track. So it's more than just the metrology instrument, but also other machine systems that deliver the whole solution. Again, it doesn't have to be the API LiDAR. It could be a surfacer. Okay, it could be the AT600. So this is what we see is the future. Now you can see that it's totally unmanned, full of operation. So 37 years of API tracker from the first generation, where the interferometers mount inside here, shooting through the gimbal and the mirror bounce off, to the latest, which is IoT. We have able to bring two IoTs here to show, and the first time we show to the public of the IoT. So if you have a chance to go to NIST and to the main building, the ground floor here, they have a museum called Artifact Museum. Then you can see the API laser tracker right there, okay? This is called the recent history, and this is called the early history. So I'm glad that they put the device here, because if they put over there, I'll be dead. Okay. Okay, thank you. Any questions?
So I was wondering, in things like microscope objectives, you have a fundamental physical limit due to diffraction. Is there any such physical limit on this instrument, and is there a need to, I guess, bypass that, or is there a way to sort of improve the accuracy of these?
Well, the limitation, is this still working? Okay. I think the IMAT basically represent a concept that the technology is unlimited. Okay, but certainly there are physical limitations, the scientific limitations. If you look at accuracies, okay, I always use the number 5 ppm is probably the limitation. Okay, can you push better than 5 ppm? Yes, but it is typically, I think, is kind of challenging. What I mean by that is that, hey, 5 ppm meaning that if I am a meter away, what's the maximum accuracies? 3D accuracies I can obtain, which is 5 ppm. If you go to 10 meters, it's 50 micron, okay, that kind of accuracy that we talk about. That is probably a boundary that's very difficult to cross. I don't believe it.
So for what reason is that boundary difficult to cross? Because of the laser itself, or because?
Well, the laser itself certainly has better than 5 ppm accuracies. Typical laser, if you like a laser inflameter, you have better than 1 ppm accuracies. But if you combine the X, Y, and the angular motion together, okay, where you will have more constraint, okay. Another one is really the environmental effect. The air turbulence, the heat distribution is not uniform. So that to me is probably the fundamental limit. So I thought of that many years ago, and I used 5 ppm as the ceiling, okay, which I think that right now is hard to surpass that.
Thank you.
Yeah, could you speak to the evolution from interferometry to absolute distance and the implications and things of that a little bit?
The interferometer is the original tracker based on, okay, it has accuracies of 1 ppm by itself. But when you integrate into the tracker with all the motion, the encoder and the geometry error of the machine, so you limit the 5 ppm. As far as the ADM is concerned, so the API ADM technology versus the Leica and Faro are different. Okay, we use time of flight technology. So a lot of people think that time of flight is not very accurate. How can you deliver that kind of accuracy? Well, we have a different time of flight concept. But eventually, the accuracies of the ADM, both at the APIs and also the other, are probably close to 1 or 2 ppm accuracies. So very close to the interferometer. So yes, that's why a lot of application right now said, if I don't need the interferometer to save money, yes, I don't want to put it there. But I think that, as I said earlier, there's a certain value when you when you're maintaining the interferometer in the tracking system where you can deliver the first tier dimensional standard. But because ADM, no matter what technique you use, the API or the Faro, they are not recognized as the dimensional standard. Okay, so you cannot use that to replace the interferometer. So there's a certain value with the tracker carrying the interferometer there. So it is in our record, we sell around 30% of laser tracking systems still with the interferometer embedded where the customer wants. Okay, so 70% people say that I don't need that traceability. Yeah.